Good afternoon. So we finally reached the last topic on this chapter, the Taylor and MacLaurin series, and the goal, as I mentioned already on the page, is to obtain a power series representation for a function f of x. So given a function, under some conditions, when can we identify this function with a power series? We already talked about the advantages of doing this, and you will see even more applications today. So I anticipate today's lecture will be a little bit longer. Make sure you have the time to sit through it, or maybe split it into two different sittings. And to be more precise, the goal is to obtain a power series representation for a function f of x centered at a real number a. Because remember, a power series, when you write it in the standard form, it's centered at a real number a. So the goal then is to write the function as the summation of c0 plus c1 times x minus a, c2 x minus a squared, so on, cn x minus a to the power n, or with the summation notation, that's summation from 0 to infinity, cn x minus a to the power n. So the idea is to actually find these coefficients, right? So the real unknown here, because the function f of x and the number a is given, typically in applications, given, or you decide basically what's going to be the number a. The idea is to find the coefficients such that you can write the equal sign between the function and the series. So you want the series, of course, to converge. This series will have a radius of convergence. That radius of convergence, the larger the better, right? Is going to be either a real number or maybe infinity, and typically the convergence will be if x is between a minus r and a plus r. So remember, radius of convergence means that the power series converges if the absolute value of x minus a is strictly less than r. That's the, or without the absolute value, you can write that inequality in this more expanded form. So you notice that there's no guarantee that this radius of convergence is really a big number. You will see some example in which is infinity, so then you don't have to worry about what you plug in for x. You can plug in any number for x. But usually you need to be careful to be within the interval of convergence given by this radius of convergence. Because some series will have a much smaller radius of convergence. For sure, it will converge at a. I mean, that's the trivial case if you think about it, right? That's going to be a constant if you replace x with a. And usually is going to be convergent for some interval around a. That interval, again, how large it is depends on that radius of convergence. We're going to focus in today's lecture on how to actually obtain these coefficients, because that's truly the unknown at this point. And then, of course, you could also find the radius of convergence, although for most of the applications today, I'm going to just take it for granted. The radius of convergence, we will basically take it for granted, and in the sense that I will mention what it is. Now, speaking about the terminology, the Taylor series, basically, it's the power series we will obtain that represents a function f of x. The MacLaurin series is just a Taylor series when a is equal to 0. We'll get to that after we go through the work on how to obtain these coefficients. So the idea is not that difficult. Here's the main condition that we need f of x to satisfy. So we need the function f of x to be infinitely many or infinitely differentiable at x equals a. So we need the derivatives. We need to be defined at a, of course, and we need the derivatives of any order to exist. Now, I want to remind you that the notation for the derivative is using this symbolic power, so that we don't confuse it with f to the power n. So this notation simply means the nth derivative of f of x at x equals a. For the first and the second derivative, we typically use, as you know already, f prime, f double prime. And then as we move along with the higher order derivatives, then we use the symbolic power. So here's the idea on how to find the coefficients. We start with what we want. So let's write again the power series that we want to represent the function with. And I'm gonna write it up to the power 4. I think it's enough to see the pattern. So I'm going to write it in the expanded form just to see the main idea on how these coefficients are obtained. And what we do, we make substitutions with x equals a. We substitute x with a in f of x and all the derivatives after that. And each time we do this, we actually find a formula for each of these coefficients. So notice if I replace x with a, then on the left hand side we have f of a, and on the right hand side we have c naught plus c1 times 0, c2 times 0. All those guys will be 0 after that. So because all of them are 0 except the first one, you in fact just found the formula for the first coefficient. So the first coefficient in this power series that represents f of x must be f of a. Then on the next step, we're going to differentiate the series. Remember, we could differentiate power series without changing the radius of convergence. And then again, replace x with a. So f prime of x. And at this point, I want you to pay attention from this point on to the patterns. So c naught disappears because the derivative of a constant is 0. The next term is going to be c1 times 1. And the next one will be c2 times 2x minus a to the first. Then the next one is c3 times 3x minus a to the second. So we differentiate by the power, right? So 4c4x minus a to the power 3, and so on. Now when we make the substitution into the derivative, we get that f prime of a, and again for purposes of seeing the pattern later, I'm going to write the constant 1 in front of c1. So it's going to be 1 times c1. And then the rest of the terms are 0. So plus 0, and so on. So c1 is just f prime of a. Again, I'm going to write it as f prime of a over 1. And let's actually mark down, just circle out these coefficients that I just find them one by one. Again, you'll see later why I just put it over 1, so you could see the pattern as we move along. Next step, differentiate one more time. So f double prime of x, now look at f prime of x, and we're going to differentiate it one more time. c1 times 1 disappears as a constant. Then we have c2 times 2 times the derivative of x minus a, which is 1. And then plus c3 times 3 times 2 times x minus a to the power 1. 4 times c4 times 3 x minus a to the power 2. I should wrote probably c4 actually in front of 4 to really see the pattern later, and so on. All right, again let's plug in a for x. So I get c2 times 2 times 1, and all of the other guys will be 0. So therefore, when I get c2 by itself, I conclude that c2 is f double prime of a over 2 times 1. And let's keep this circled. And one more. Let's do one more. Look at f double prime. We differentiate one more time. So that's going to be the third derivative with respect to x. Again, c2 times 2 times 1 is a constant. That goes away. Then I'm left with c3 times 3 times 2 times 1 plus c4 times 4 times 3 times 2 times x minus a, and all the other terms, each of them will contain x minus a to the first, to the second, and so on and so forth. So notice each time you differentiate, you have a constant in the beginning of the summation, and all the other terms will contain x minus a. So that when you plug in a for x, you're going to get just the constant in front of the summation, and all the other terms will be 0. So then finally, C3 from this equality is going to be the third derivative with respect evaluated at a over 3 times 2 times 1. All right, so if you notice, if you look now from top to bottom to the C1, C0, or maybe from C1 is going to be maybe easier to see. So if you look at C1, you look at C2, you look at C3, I hope you see some pattern. Notice that on the bottom we have 1, 2 times 1, 3 times 2 times 1. These are just factorials. So 2 factorial is 1 times 2, 3 factorial is 1 times 2 times 3, so all the numbers up to 3. So that means the pattern is basically that Cn, the formula for Cn, is the nth derivative evaluated at a over n factorial. Now notice this includes C naught because when n is 0, that's like not having any derivative, so just f of a by itself, over 0 factorial, and you might remember that by definition 0 factorial is 1. One of the reasons why we actually use that convention, so we can have the same formula for, you know, terms like this, so that we have a single formula for the coefficient. So it's as simple as that. This is the representation of a function in terms of a power series. The coefficients must be given in terms of these derivatives over n factorial. And again, this doesn't answer whether it converges or not. Each of them will have a certain radius of convergence, which has to be computed separately, as we did already in a previous lecture, right? Where you have a power series and you can determine the radius of convergence using the typically the ratio test. Then you could find the interval of convergence to check the bound endpoints of that interval, a minus r, a plus r. And many of the important functions are already given in the table in terms of these series, so that you don't have to compute them again, together with the radius of convergence. So let's move on the second page with writing in a more compact form this formula, and we'll move on with some examples after that. All right, so we obtained that f of x as a power series is written as f of a plus f prime of a over 1 factorial times x minus a. I'm just writing those coefficients. Plus f double prime of a over 2 factorial x minus a squared. In general, f the n derivative of a over n factorial x minus a to the power n. Or again using the summation notation, like that. So this is what we call the Taylor series centered at x equals a for f of x. So each function will have its own Taylor series. And if a is equal to 0, so if you decide the function to be centered at 0, I mean the series to be centered at 0, this is called the MacLaurin series. So that's going to be just x to the n and so on. So the MacLaurin series is just a Taylor series centered at the origin, at 0. So this will be the MacLaurin series. Many tables will give you the MacLaurin series for f of x. And of course, together with a radius of convergence. We'll talk about that in a minute. One important observation is that whenever the function has a Taylor series representation like this, Whenever you look at the first n terms, so if you basically look at one of these partial sums, you obtain what's called a Taylor polynomial. So in other words, if you decide not to use an infinite sum, but just the first n terms, however you want it to be, like the first 2, 3, and so on, you obtain a polynomial, obviously, because you stop at a certain power. So this will be the nth degree polynomial, Taylor polynomial. And this polynomial will approximate the function, so approximates f of x for x near the center of the series, near a. So I'll show you with some examples on Maple how you can basically approximate the original function f of x with these Taylor polynomials. As you might guess, the more terms you add in these polynomials, the better your approximation is. This is an extremely important and useful concept or application of Taylor series. One of the major applications which you will see playing a role, for example, in the analysis of differential equations, is the so-called linearization. So sometimes the problem or the function is so difficult that it will be useful to approximate it by, let's say, a linear term, or maybe a quadratic term, which is harder than a linear term, but still maybe easier than the function itself. So Taylor polynomials will give you this way to approach the problem. So you decide and say, okay, I have a function that I cannot handle, but I can handle a quadratic, let's say, so a function of degree 2. Then you could simply replace f of x with the second degree Taylor polynomial if you are okay with this approximation. And this approximation will be good, or it will be as good as, let me put it differently, it will be good if x is as close as possible to a. So the farther you are from the center, the bigger the error is, essentially, or tends to be. You're guaranteed to have a good precision or good approximation if you use this approximation for values as close to the center as possible. So it's basically an approximation that is useful at a local level, in some interval around the center of this series, that number a, which is the reason why it's good that you can actually decide what the value of a is, like what is the center of this series. Because, for example, if you want to use, for instance, the function for values close to 1, let's say at 1.1, let's say you want to use the function to approximate the function values like this, then it makes sense to choose a to be 1, because then you can plug in values closer to that center. You could use it for any number as long as it's convergent or in that interval, but again, the error could be much bigger. So with that in mind, let's actually move on with a couple of examples. And the first example is on how to compute this Taylor series from scratch. Like, just computing these coefficients, these derivatives, and hopefully seeing a pattern. And we're going to start with perhaps one of the easiest functions to do this. Let's do the Taylor series for e to the x centered at 0. So let's do basically a MacLaurin series for e to the x. That means a is equal to 0. So what I like to do, well, we'll do that later actually. I like to do a table when the derivatives look different enough so that I can see maybe a pattern. In the case of e to the x, things are much more straightforward because the derivative of e to the x is just e to the x. So when I look at the formula for the coefficient on those terms in the series, well, the end derivative of f of x, in this case, e to the x, is just e to the x, right? So it doesn't matter how many times you differentiate e to the x, you still get e to the x, right? So the derivatives are all the same, no matter what the derivative order is. So I meant here e to the, the end derivative at 0, right? Because we want a MacLaurin series. So on one hand, the n derivative is just e to the x, and evaluated at 0, that's going to be just e to the 0 and then over n factorial. So in the case of e to the x, the Taylor coefficient is 1 over n factorial. So you could write e to the x as the summation from 0 to infinity 1 over n factorial x to the n, or in the expanded form, that's going to be 1 plus x over 1 factorial, x squared over 2 factorial, x to the n over n factorial, and so on. And it's easy to see, we could check that if you want with the ratio test, that the radius of convergence is infinite. So as it happens, this MacLaurin series is defined for any x. If you write this summation into Maple or something similar, Maple will recognize it as being e to the x. So this is truly the equality of two functions. They are essentially the same thing. That's one of the main things to keep in mind from this point on. It is equal e to the x with this infinite sum for any x, because the radius of convergence is infinite. And let's move on with other examples on the next page. All right, so let's do another MacLaurin series. That's at x for the function sine of x. Again, so we're looking for computing the n derivative at 0 over n factorial, which is multiplied by x to the n, right, in the Taylor series. What I like to do in problems like this is to kind of organize myself in a table. So here on the first column, you're going to basically compute the derivatives, because remember, you have to compute the derivative first before you plug it in. And then in the next column, you're going to have the derivative evaluated at a, which is 0 in my case. And then the actual coefficient, the derivative of, with respect to n at 0, not with respect, the n derivative at 0 over n factorial. Because once you compute that, then you can plug it in into the summation and you're done. Now, you should do this basically until you kind of see a pattern, because in most of the problems that you will encounter, you will see a pattern on these coefficients. And then once you see the pattern, you can just write it down in, you can just find basically the general formula for that coefficient, for the Taylor coefficient. And here, just indicate the value of n when you do these computations. So n equals 0, n equals 1, and so on. So n equals 0 means that the function is just the function itself without any derivative. So that's just sine of x. Then you're going to plug in 0 for x, and that's 0. You could write just 0 right away. I just write sine of 0 just to see where it comes from. And then, of course, it's going to be that value over 0 factorial, which is 0 over 1, which is 0. So basically, the first Taylor coefficient is c naught equals 0. Then on the next level, when you move on to n equals 1, you just differentiate the above, right? Because above was f of x, now is f prime of x, so that becomes cosine of x. Evaluated 0, that's 1. 1 over 1 factorial, that's going to be 1 as well. And that means c1 equals 1. Moving on, n equals 2. Actually, another thing to keep in mind, you might actually want to leave it as 1 over 1 factorial. So don't rush to simplify, because you may not see the pattern, basically, if you simplify too early. N equals 2 means the derivative of the above, that's minus sine of x. At 0, minus sine of 0, that's 0. Here I'm going to have 0 over 2 factorial, which is 0, so c2 will be 0, or 0 over 2 factorial. Let's keep both to see later whether it helps or not. N equals 3. The derivative of the above, that's minus cosine of x. That's going to be minus 1, minus cosine of 0. So minus 1 over 3 factorial. So I'm going to leave it like that. C3 is then minus 1 over 3 factorial. Let's do one more. N equals 4. The derivative of the above is minus minus sign, that's sine of x. Sine of 0 is 0. 0 over 4 factorial is 0. C4 is equal to 0. Now, you should notice that because of the nature of these derivatives of sine of x, the values will be repeated. The derivatives will be repeated after this step. So I have sine of x, cosine, minus cosine, and then sine again. So if I continue with the derivatives from this point on, they will be repeated. You're going to have again sine, minus cosine. So the values on the top of these fractions on the right hand side will be repeated. What's different is the factorial, because as you move along, you're going to have basically n factorial at some point on the denominator here. And on the top, you just have these values 0, 1, 0, minus 1, cycling through, and so on. So let's see how we could write this in a maybe nicer way as a pattern. Notice first of all that if n is even, then Cn is equal to 0. So all the even terms are actually 0. C0, C2, C4. So you could choose to not even write them down. Whenever you want to represent only the even or the odd numbers, one typical way to do that is to write, for example, 2n, as n goes from 0, 1, 2, 3, and so on, and 2n plus 1 for the odd numbers. So the even numbers are 2n, and if n goes from 0 to 1, 3, then 2n is 0, 2, 4, 6, and so on. Whereas 2n plus 1 goes to all the odd numbers. Again, n is the same from 0 to infinity, but if you just write 2n plus 1 instead of n, you go through the odd numbers only. Because this is what you should have essentially in your Taylor series. So basically, if you write it term by term, the first non-zero one will be 1 over 1 factorial x to the first, that's when n equals 1, right? And then the next non-zero one will be for n equal 3, so the next one will be minus 1 over 3 factorial x to the power 3. And now you should see the pattern, right? The next one will be plus 1 over 5 factorial x to the 5th, and so on. When you write it as a summation, again, n will be from 0 to infinity. You're going to have obviously the odd terms only. So you have 1 over 2n plus 1 factorial x to the 2n plus 1. But you also have a cycling through a signs, plus, minus, plus, minus, plus, minus. Whenever you have an alternating series like this, remember from alternating series, that alternance can be written as minus 1 to the n or minus 1 to the n minus 1 or minus 1 to the n plus 1 if you want. N or n plus 1, depending on whether you want to start with a minus. Actually, this will be minus 1 to the n, sorry. Depending on whether you're going to start with a positive number or a negative number. So when n is equal to 0, I have a positive number, 1 over 1 factorial. So it's minus 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. So again, when you look at an alternance of signs, you're looking at minus 1 to the n or minus 1 to the n plus 1 or minus 1 to the n minus 1, depending on the starting value of n. But it's one of these two, depending on whether you start with plus or minus. You just have to basically double check. So if n equals 0, minus 1 to the 0 is plus, and then the next one will be negative, and so on. Typically, if you check the first two terms to see if they match, that's like a control check. You could do that, basically. So anyway, this is the MacLaurin series for sine of x. You will see this result, for example, on books, in various books, including, in various calculus books, you have already the MacLaurin series given to you. We're going to do another example like that, and then we'll move on to other topics on the same lesson. All right, so this is my third example. Let's do one which is not centered at 0. Let's do for natural log of x, centered at a equals 1. And again, remember, we're looking for the coefficients and derivative at a over n factorial, which, of course, in the summation is multiplied by x minus a to the n. And let's do that table again. So we're going to have a column for the n derivative, then that evaluated at 1 actually, because a is equal to 1. And then the actual coefficient, the n derivative at 1 over n factorial. So starting with the function itself, which is ln of x, evaluated at 1, that's going to be 0. And then 0 over 0 factorial, that's 0 over 1, that's 0. Moving on, n equals 1, the derivative is 1 over x. Evaluated at 1, that's 1 over 1, which is 1. That's the derivative. And that derivative is divided by 1 factorial, which is 1, but we'll keep it. Right, so this is c naught, this is c1, and so on. For n equals 2, if you can't do it directly, write it as a power. So write it somewhere as x to the minus 1. But after that, just write it in a simplified format. So that's minus 1 over x squared, the derivative of the above. Evaluated at 1, that is just minus 1. And then that's divided by 2 factorial. So that's minus 1 over 2, which is my second term in the series. And we do that until we're confident we see a pattern. The third derivative will be 2 over x third. Please do that separately if it's not clear. And then evaluated at 1, that's equal to 2. And then that's divided by 3 factorial. And let's keep it like that with factorial, but also let's simplify it, because again, you may see the pattern differently later, right? So 2 over 6, 3 factorial is 6, right? 2 over 6 is 1 over 3, and that's the third. That's C3. Let's do one more. N equals 4, the derivative of the above is going to be minus 6 over x fourth. Plug in 1. That's the derivative, so that's divided by 4 factorial, which is 24, and that simplifies to minus 1 over 4, and that's C4. So at this point, you should probably see the pattern. So let's look at the coefficients. Let's look at the coefficients without the factorials, because I think you can see the pattern over there. You start with 0, then it's going to be 1, which, to make it look like the rest of them, let's say it's 1 over 1. So 1 over 1, second one is minus 1 over 2, the third one is 1 over 3, the fourth one is minus 1 over 4. So in general, it's going to be 1 over n with some alternates of signs. And by the way, the first one is 0, so we don't have to count this one. I mean, we can start the summation from 1 to infinity, because the first one is 0. And then, just like before, we have the first guy with plus, and the second one with minus, the third one with plus, the fourth one with minus. So pause the video for a moment and ask yourself, is it minus 1 to the n, or maybe minus 1 to the n minus 1? Okay, so it should be obvious that if you start counting n from 1, and given the fact that the first one should be positive, then it's going to be minus 1 to the n minus 1. You could write n plus 1, that achieves the same thing. The whole idea is to actually have the first sign correct. So we can expand this and say ln of x is 0 plus 1 times x minus 1 minus 1 half x minus 1 squared plus 1/3 x minus 1 to the power 3 minus 1/4 x minus 1 to the power 4, and so on. Or in a more compact form, the summation from 1 to infinity minus 1 to the n minus 1 over n times x minus 1 to the power n. So that is the Taylor series centered at 1 for natural log of x. We're gonna use this one for a graph later, just to see how it approximates the actual natural log. So I'm gonna have after this lesson a little video with Maple just to see the Taylor polynomials together with the function they approximate. We're gonna do another example just like this. An example which I don't insist too much, but it's still kind of useful, in which in the function itself that we need to write it as a Taylor series is a polynomial in itself, because in that case we have kind of a special situation, as you will see immediately. All right, so what if the function itself is a polynomial? Well, you might already guess that the series is no longer really an infinite sum, because at some point all derivatives will be 0. Because each time you differentiate a polynomial, you reduce the degree, and then eventually it's going to be 0. That doesn't mean it's useless, and it doesn't mean it doesn't fit the definition of a Taylor series. The only thing is that all the terms of the series are 0 except the first ones. So let's follow again the definition, constructing the series like before. So just like before, we start with the function, the derivative of the function in the first column, the derivative evaluated at minus 2 this time, because that's what a is equal to, and then that value divided by n factorial. So the function itself is x fourth minus x squared plus 1. And then when I evaluate that at minus 2, that's going to be 16 minus 4 plus 1, which gives me 13. And then it's 13 over 0 factorial, and that's going to be equal to 13. 0 factorial is 1. So that's the first coefficient. When n equals 1, the derivative of the above is 4x third minus 2x. Plug in minus 2, that's 4 times minus 8, that's minus 32. And then plus 4 makes it minus 28. Then that's divided by 1 factorial, that's minus 28. N equals 2, 12x squared minus 2. At minus 2, that's going to be 48 minus 2, which is 46. And then that's divided by 2 factorial, which makes it 23. And n equals 3, 24x. At 2, that's 24 times 2, which is 48. Over 3 factorial, which is 6, 48 over 6. No, sorry, minus 2. Minus 2. That's minus 48. Minus 48 over 6, that's minus 8. N equals 4, that's 24. That's a constant, so when we evaluate it at minus 2, it's still 24. And that's divided by 4 factorial, which is another 24, so that's equal to 1. From this point on, all the other derivatives are 0. So basically, Cn is going to be 0 for n greater than or equal to 5. So the so-called Taylor series in this case is essentially just the same polynomial written differently. It still fits the definition and it's still useful. Let me actually start from here so I can fit it. Well, I'm going to write it actually. It's going to look maybe weird, but I'm going to write it here down on the bottom of the page. So x fourth minus x squared plus 1 is equal to the first term. So that's C1, C0, C1, C2, C3, and C4. So it's going to be 13 minus 28 times x minus a, in my case now is x plus 2. Notice this as well. So it's minus 28 times x plus 2. Then it's plus 23 times x plus 2 squared. Minus 8 times x plus 2 to the power 3. Plus x plus 2 to the power 4. And then the rest of them will be just 0, which we won't write them down. So you may wonder one thing at this point. What good all this does? Because after all, you just replace a polynomial of degree 4 with another polynomial of degree 4. You just wrote a polynomial in a different way. So for example, if I expand and simplify, well, you can just get this polynomial. It's not hard to guess that that's the case. So this is no longer essentially an infinite sum in the sense we learned already, because all the terms are 0 except the first 5 terms, if you include 13. This is still useful though, so let's write it here as a remark. So this is useful if you want a lower degree. So let's say for the application that you want to do, some sort of approximation or whatever you want to do with this function, let's say this degree and 4 is hard, right? I mean, it's a difficult thing to deal with. But let's say you're happy with a quadratic. Then as long as you use x values kind of close to minus 2, which is, remember, the center of this representation, you could just basically replace your 4th degree polynomial with a 2nd degree polynomial. And that'll be a good approximation if you maintain the x values as close as possible to minus 2. So there is still a useful, there's still a use of a Taylor representation for a polynomial, although that Taylor representation is nothing but, at the end of the day, rewriting the polynomial in a different way. So that's one item out of the way. Let's do the next couple of examples will be on how to use, for example, tables of Taylor series already determined, or MacLaurin series, and how to use those tables to obtain other MacLaurin series so that we don't have to go through this trouble of computing these coefficients one by one, which could be actually hard in some situations. So let's stay tuned for the next page. All right, so a typical question is using a table of a MacLaurin series, tables that are basically given in many books, many textbooks, obtain MacLaurin series for the following functions. So we're going to do 2 examples like this. It's pretty straightforward. You basically want to substitute essentially what you have in your function for one already given in a MacLaurin series table. And then also being aware of the radius of convergence. If that changes, you have to basically specify it so that you're aware under what conditions your series is valid. So for example, the table may contain the expansion of MacLaurin series expansion for cosine of x. We did for sine of x ourselves earlier. For cosine of x, the expansion is summation from 0 to infinity minus 1 to the n x to the 2n over 2n factorial. So actually this goes to the even powers, unlike the sine one. So if you expand this one, that's just 1 minus x squared over 2 factorial plus x fourth over 4 factorial and so on. The radius of convergence is infinite, so converges for any number. So for example, let's say we want to obtain the same for the function x times cosine of 2x. So what you have to recognize is the fact that you could use the representation for cosine of x, except that in your problem, your function is cosine of 2x, which means you're going to replace x with 2x into the Taylor expansions for cosine of x into the MacLaurin expansion. And you do that using the summation notation to be more practical. You don't need to expand, use this expanded format. So all you have to do is to multiply x by the equivalent of cosine of 2x via that series. So summation from 0 to infinity minus 1 to the n. Pay attention here, 2x to the power 2n over 2n factorial. Get this out of the way. So just replace x with 2x in that series. And then any power of x outside the summation, you can bring it into the summation and then rearrange maybe the terms a little bit to make it look like a true power series. So this will be summation from 0 to infinity minus 1 to the n. You want to separate to the 2n by from x to the 2n, which is again multiplied by the external x over 2n factorial. Because again, we want to write everything as a power series with coefficients times x to a certain power. So we have minus 1 to the n, 2 to the 2n over 2n factorial. This is the coefficient. And then combined x to the 2n plus, times x, that's just x to the 2n plus 1. So that's the MacLaurin series for x times cosine of 2x, using, again, an existing series in the table. That's why tables give you this MacLaurin series for the most important functions. Here's another example. I lost count actually with the examples, but let's say we want the same for x squared times natural log of 1 plus x third. And as it happens, the table contains the expansion for natural log of 1 plus x, which is summation from 0 to infinity, from 1 to infinity, I'm sorry, from 1 to infinity minus 1 to the n minus 1 x to the n over n. And here the radius of convergence is 1. And actually I'm going to do just a similar one to this one just to see the difference here. So just like before, you're going to replace, we have ln of 1 plus x third in our problem. And we have the table for ln of 1 plus x. So all we have to do is replace x with x third in this series and plug it back into the function itself. So ln of 1 plus x third can be replaced by the summation from 1 to infinity minus 1 to the n minus 1 x third to the n over n. Bring inside the x squared. And here we're going to have x to the 3n plus 2 over n, right? So x to the 3n plus 2. Now, because you replace x with x third and the radius of convergence is 1, remember that means the series is valid for absolute value of x less than 1. Which means when you replace x with x third, you have to make sure that x third is now between 1 and minus 1. So whatever you plug in for x into the MacLaurin series in the table must be within the same interval of convergence between those values, 1 and minus 1 in this case. Now here we can take, because absolute value of x to the power 3 is the same as absolute value of x to the power 3, I mean the absolute values to the 3, we can take the cube root, and as it happens, the radius of convergence ends up being the same. But it's important to point out that the radius of convergence need not be the same, depending on what you plug in. So let's do another quick example related to this. So what if I want to find, for instance, the expansion, the MacLaurin series for ln of 1 plus 2x? That's an immediate application of that formula. Just replace x with 2x. And again, you can separate 2 to the n if you want, like that. But again, if the table formula is valid for absolute value of x less than 1, whatever you replace x with, in my case 2x, needs to be less than 1 in the absolute value. So without the absolute value, you need 2x to be minus 1 and 1, which is to say you need x between minus 1/2 and 1/2. So as it happens, here the radius of convergence is going to be 1/2, not 1 as in the formula. So bottom line, when you substitute x with something else in the formula in the table, make sure you do that also in the conditions which indicates the radius of convergence. If the radius of convergence is a number, obviously, because if it's infinite, you don't have to worry about that. So let's stay tuned for yet other applications of these on the next page. So here's another type of application. I think we did something similar before. Let's say you want to approximate a number within 5 decimals. So in this case, I think it's not clear what I wrote here. So it's going to be 1/10th root of e. So some crazy number like this. So here is just a matter of matching the number with a function for which you know the MacLaurin series or the Taylor series in general. So in the table, you typically have, for sure, you're going to have the expansions for e to the x, because that's one of the important functions, right? So it's the first one we established ourselves as well in this lecture. So we know we have this Taylor series representation, radius of convergence is infinite, for e to the x. So if you look at the function itself, e to the x, and the number you want to approximate, you see some connection in the sense that you can write your number as a power of e. So 10th root of e is like 1/10. I mean, it's e to the 1/10. So 1/that is e to the minus 1/10. And minus 1/10 is kind of close to 0. And remember, the MacLaurin series is centered at 0. So that tells me if I replace x with minus 1/10 into the MacLaurin series, I probably get a pretty good approximation if I just add a bunch of terms. So basically, you replace x with minus 1/10 in one of the Taylor polynomials. Now, what Taylor polynomials you need? Well, it depends on how good the approximation you want it to be. In this particular case, so this is going to be minus 1/10 to the power 3. In this particular case, if you add all of them up to the power 3, actually up to the power 4. So let's write 2 more. I did this with the calculator earlier, so you should, by the way, check these values as well. So if you actually plug in minus 1/10 into this Taylor polynomial, you will notice that by the time you reach the 5th power, so check this with the calculator, this is actually going to be approximately equal to 8.3 times 10 to the power minus 8. So lots of zeros after the decimals, basically. So that means all the terms up until the 4th power together are within 5 decimals for sure. So in fact, this summation is going to be equal, again, you can run it with Maple or with a hand calculator, that's going to be equal to 0.90484, which is essentially your approximation of e to the minus 1/10. Because this is an alternating series, remember, each term gives you the error of adding the previous terms. So the 5th term having so many zeros after the decimals, like 7 zeros, that means you are for sure within 5 decimals by the time you add the 4th power there. If you're happy with a smaller error, you just add fewer terms, basically. So the idea is you plug in the value for x, which is close to the center, in this case 0. So that's why in this case this MacLaurin series can be used to approximate this quantity. Two more applications before we call it a day. We could use Taylor series to calculate, for example, integrals that otherwise are hard or impossible to compute. So there are entire branches of mathematics, like for example, partial differential equations methods of solving, in which it's impossible to use classical functions to solve the problem. So instead of the function itself, you use its power series representation, or the MacLaurin series. So the trade-off is that your answer won't be a classical function, will be a series, but it will be just as good in the end, right? Because it's the same as, I mean, that's the exact answer in the end. It's just in terms of a series. So here's an example. Let's say you want to integrate inverse tangent of x squared. That's a difficult problem, maybe impossible to do by classical means. But if we cannot do it by classical means, instead we can replace inverse tangent of x squared by its MacLaurin series. Especially if you want to evaluate this integral at boundaries close to 0. I mean at bounds close to 0. And the table of MacLaurin series gives you the fact that inverse tangent of x is actually the summation from 0 to infinity minus 1 to the n x to the 2n plus 1 over 2n plus 1. So you have that in the table. So all you have to do inside the integral is to replace inverse tangent of x squared with the series representation for the same function. So that means in the Taylor series representation for inverse tangent of x, you're going to replace x with x squared. And then after you separate the constants, so let's see, we have 1 over 2n plus 1 and then x to the power 4n plus 2. Then you're going to integrate inside the summation. So the integral of a sum is the sum of the integrals. Any constant with respect to x is outside of the integral. And it's just a matter of integrating then x to the power 4n plus 2 dx, which is just the power rule. So power rule x to the 4n plus 2 plus 3, I'm sorry, 4n plus 2 plus another 1 over 4n plus 3 plus a constant of integration. So this is your antiderivative of the inverse tangent of x squared, which is written in terms of a series. Now, the last topic is really not that important. You may have maybe at most one example like that in exams or quizzes, but because usually there are other ways to go about it, but it's just yet another application of Taylor series that you might want to be aware of. A quick way to use them in order to estimate limits. So to compute limits, you can use MacLaurin series to quickly compute limits in some situations. So let's stay tuned for hopefully the last page. All right, so I wrote here again the expansion for ln of 1 plus x and sine of x to have them in front of me. So this type of application is when the limit contains powers of x and maybe another function for which you know it's a Taylor expansion, let's say. So in this case, notice that, by the way, first of all, this is a 0 over 0 case. You could do it with L'Hopital, so that's why I'm saying it's not really that overly important, this application, but it's still an interesting application of Taylor series. So you could do, instead of L'Hopital, you could replace ln of 1 plus x with its MacLaurin representation, because you see x approaches 0, so obviously it makes sense to approximate the function via its via some Taylor polynomials, MacLaurin polynomials centered at 0. So you want to write not the summation in this case, but actually the first bunch of terms, enough of them to account for all simplifications that you may do here with the other terms in the limit. So pay attention to what I mean by that. So we have x minus, and now look at the expansion for ln of 1 plus x. And I'm going to write the first term, which is minus 1 to the 0, x to the 0 over x to the first over 1, right? So that's just x. The next term is going to be minus x squared over 2. Then the next one will be x third over 3. And minus x fourth over 4. And at this point, you should realize that all the other terms won't matter because you have enough to account for all possible cancellation. See, the reason you have 0 over 0 on the top is because of that cancellation, basically. What I mean is that the linear terms will cancel. So you have x outside the natural log, so you have to account for that. And also have to account for the power of x on the bottom, because you need to simplify by that as well, so that you won't have a 0 over 0 case. So in other words, you need to write enough terms in the series so that you eliminate the 0 over 0 case, which is the undeterminate case in this limit. So you don't have to write the full summation, but you still have to do some algebra here. So let's first of all eliminate that parenthesis. So it's x plus x, x minus x plus x squared over 2 minus x third over 3 plus x fourth over 4 and minus and so on over x squared. X with minus x cancels. On the top I can pull now, if you look carefully, I can pull out x squared. This is going to cancel with the bottom one. And you're left with 1 over 2 minus 1 over minus 1 over 3x plus 1 over 4x squared and so on. And then finally you end up with the limit, which is no longer indeterminate, so you can just compute it. So all the terms will have x to a certain power, which means they will approach 0. So as when you pass the limit, as x goes to 0, you're just left with 1 over 2. So the limit of x minus ln of 1 plus x over x squared is just 1 over 2. So here's another quick example, and that's going to be the last one. So let's say you have limit as x goes to 0, sine of x minus x plus x third over 6 divided by x to the fifth. So again, the key thing is to replace sine of x with its MacLaurin expansion. Just again write enough terms to account for all simplifications. So I should see probably at least up to power 5, if not more, to see the pattern, right? Because I need to simplify it with the x to the fifth on the bottom as well. So sine of x, the first term, minus 1 to the 0 is 1. So the first term is going to be x over 1 factorial, which is just x. Then it's going to be minus x third over 3 factorial plus x fifth over 5 factorial. And let's write another one, and that's it. Dot, dot, dot. That's the series. And then is going to be minus x plus x third over 6 divided by x to the fifth. Now notice again, x to the x cancels with minus x. 6 is nothing but 3 factorial. So plus this goes with minus x third over 3 factorial. And on the remaining terms, you can pull out x to the fifth in anticipation for the cancellation with the bottom. So you're left with 1 over 5 factorial minus 1 over 7 factorial x squared. The next one probably will be 1 over 9 factorial. If you see the pattern, x fourth. All of them will have x to a power. And so when you pass the limit, this chunk goes to 0, and you're left with 1 over 5 factorial, which is also 1 over 120. 5 factorial is 120. All right, so these are all the applications I want to present in this lecture. Please don't be patient and allocate as much time as possible to this lecture. Well, hopefully you did that already by this point, because you will see this topic actually popping up in other courses later, depending on your major, of course, but it's an important topic for later. So that's it for today.